Here we go. Okay, welcome to the Geometry and Model Theory seminar. Today's speaker is ready to go. Ari Shaviv from Princeton, and he will tell us about the Schwartz spaces.
Okay, first, thank you, Patrick. Thank you, Tamara. Thank you, all the other organizers, for inviting me to give this talk.
Ari,
Do you hear me?
can you make it a bit louder?
Oh, louder. Yes. Okay. I will just speak louder.
Yeah.
Okay. So thank you for inviting me to this talk. Thank you, Patrick, Tamara, everyone. So I will talk about Schwartz spaces, and I will try to focus today on a very specific question that I find very interesting. Hopefully, some of you will also find it somewhat interesting. And I will introduce it in a second. So I will just say that I don't see the chat. So if you want to ask something, please unmute yourself and just ask. So let's start with what are Schwartz functions. So, okay. So the setting will be mainly Schwartz functions on open subsets of Rn. So we fix an open subset of Rn. We have no assumptions on this set for now. And before we define Schwartz functions on this subset, let's define Schwartz functions on Rn. So Schwartz functions on Rn will be C-infinity smooth functions. Let me just change something in my view. Okay, never mind. So these will be C-infinity smooth functions on Rn that have the following property. So if we fix any two multi-indices, so alpha and k will always be n-dimensional if you want multi-indices. So these are just n tuples of non-negative integers. This quantity is finite. The supremum of this expression is finite. So let's unfold this expression. You will see many times these expressions in this talk. So if we take f and we take the alpha derivative of it, so for instance, think about alpha equals all zeros. So we just look at the function f. And we multiply it by any monomial. So when I write x to the k in this language, so x is an n-tuple and k is also an n-tuple. So x to the k is just a product of x1 to the power k1 times x2 to the power k2 and so on. So if you look at any partial derivative of f and we multiply it by any monomial, this quantity on the entire Rn is finite. So if you want, we have functions that decay at infinity. They go to 0 at infinity, very fast, rapidly decaying, because even if we multiply them by any polynomial, they still decay. They still go to 0. And also all the derivatives have the same property, right? So if you want to think of a concrete example, you can think of a Gaussian on right, the normal distribution on R1. So that's like a typical example. So these are Schwartz functions on Rn and Schwartz functions on Ru. So now we have this open subset of U. We have this expression. So let's unfold this weird expression. So we take all Schwartz functions on Rn that satisfy the following condition. So at any point z outside of U, we look at our function f and all of its partial derivatives, and we evaluate it at the point z. So, and the condition will be that our f and all the derivatives at any point outside U is 0. So in other language, these are C-infinity smooth functions on Rn that first has the rapidly decaying with all derivatives condition from being Schwartz functions on Rn, right, at infinity. And also the Taylor series of our f at any point outside U should be identically 0. Okay, and we will call such functions flat at the point z. Okay, so these are Schwartz functions on U. Before we start doing things, let's say a few remarks. So first, the Schwartz space of Rn is a Frechet space, and it's really not important what's a Frechet space. The important thing for us will be that it's not just a linear space; it's a topological space. So we can talk about, for instance, linear functionals, but also about continuous linear functionals. So that's the first remark. And here I gave the explicit definition of the topology by this countable family of seminorms, but it's really not important. If you don't want to think about Frechet spaces, that's fine. The second remark is that if you look formally at the definition of Schwartz function on U, it's a Schwartz function on Rn that satisfies something, right? But usually we just think of elements in this space as smooth real-valued functions on U, such that if we extend them by 0 to a function on Rn, it's a Schwartz function on Rn that satisfies some condition. Okay, so naturally we think of S of U as a space of functions on U. Okay, that's a very formal remark.
Yeah. Sorry, Ari, Jean-Philippe.
Yes.
Yes, a little question. So if, for example, your open set U has a boundary, does it imply something when Z goes to the boundary on the behavior of the function F? Yes.
Yes, exactly.
Okay. Exactly.
So let me say it here, and I will repeat it in a slide or two. So it means that your function F, you can look. So if Z is a boundary point, we look at the Taylor series at Z, and you can calculate it by the behavior of your function inside U, right? Because Z is a boundary point. So it tells you that it decays really fast, and all the derivatives decay very fast. But in, I think, 2 or 3 slides, we will have an equivalent definition that doesn't see the derivatives. That's a very good question because it helps me.
Thank you.
Thank you. Good. Great. So if there are more questions, just ask. Many questions is good. It means that people are alive and with me. Okay, so that's the second remark. And the third remark, it's more like okay. It's again, it's not super important, but it's important if you really want to do stuff with these functions that we will not do today. If we take an open subset U that happens to be an open subset of a different open subset V, both live in Rn, then we can take any Schwartz function on U, which is the smaller space, and extend it to a Schwartz function on the bigger space, right? Because the definition of SU consists of many conditions on the complement to U, right? So if on the complement of U you have many conditions, in particular in the complement to V you have many conditions, right? So this is the other way, if you want, of many spaces of functions have the different direction, right? So for instance, if you look at continuous functions on some space and you restrict it to a smaller space, you get a continuous function on a smaller space, right? But here the behavior is the other way around, right? And if you really want to give it a name, so instead of having a pre-sheaf of functions, we have a pre-co-sheaf of functions because the arrows go in the other way. Again, it's not super important for today, but okay. So that's the basic definition. Now we have this proposition. And as Jean-Philippe said, we can instead of thinking, so let's take a Schwartz function on Rn, and let's assume that if we're restricted to the complement to U, it's identically 0, which is an easy condition to check. Now we have this equivalent condition that's saying that Rf is a Schwartz function on U, namely the Taylor series is identically 0 at any point outside of U. If and only if Rf decays really fast as it approaches the boundary, namely not just the supremum is bounded, the supremum of the function itself is bounded, but even if we take the distance to the boundary, right? This function in the denominator is the distance to the boundary, and we take very high powers of this distance, still we get a finite quantity. The supremum is still finite. Okay, and this already guarantees that the derivatives will also go to 0 at any point in the boundary and so on, all partial derivatives. So this is the first proposition, and I will not prove it now, but I hope it's believable, right? So this is an equivalent property, which is sometimes easier to work with because you see, condition 2 doesn't involve the derivatives of f at all. Okay. So that's the proposition, and now let's state the main definition that we will discuss today. So if we have 2 open subsets, they are Schwartz equivalent if we can find a diffeomorphism, and diffeomorphism for me is always C infinity diffeomorphism, between them, such that this diffeomorphism induce an isomorphism between their Schwartz spaces. Okay, so we look at all Schwartz functions on V. We can define a new function, just f function on U, by first apply phi and then apply your function. And if this happens to be a map between the Schwartz spaces, and not just a map, but an isomorphism between the Schwartz spaces, then we're happy and we say, okay, these two sets have the same Schwartz space in a sense, and they are Schwartz equivalent. And the main theme of today's talk will be when the two open sets have the same Schwartz space. When can we find such a phi? Now let me start with a non-example. Okay, so for instance, is the definition clear? Does it make sense? It's quite straightforward, right? Now let's see a non-example. So let's look at the exponential function from the real line to the positive ray. So this is a C-infinity diffeomorphism between the real line and the positive ray, but it does not induce Schwartz equivalent, right? Let's see why. So let's look at the right-hand side. We take a function. Let's say it is 0 from some point on to the left. So we don't care about this side. And let's say that at infinity, it behaves like e to the minus x. So this is a nice Schwartz function, right? It's believable if we take this function and we take any derivative, and even if we multiply by any polynomial, still it's bounded. But what happens if we take pre-compose it with the logarithm function, right? Which is pooling this function using exponent, right? It's very confusing. Saying pooling and pushing is very confusing to me. So I randomly say pull or push, and sometimes it works. Okay, but hopefully you understand what I mean. So let's try to pull it with the exponential or push it. Okay. So we first apply the logarithm function, right? So we want a function on the positive ray. So we first apply the logarithm function and then apply this e to the minus x at infinity behavior. So, right, so we did it here and we get a function that decays at infinity like 1 over x, right? And a function that decays like 1 over x is not Schwartz, right? Even if we just multiply it by the polynomial x or x squared, it's not bounded, right? So this is a non-example. However, these two open sets, the real line and the positive ray, are Schwartz equivalent because we can choose a different diffeomorphism. So the exponential is the bad choice here. We can take this diffeomorphism, and hopefully it is a diffeomorphism between the real line and the positive ray. I calculated a few years ago, and since then I used this example, but I didn't check it for a while. And this is a C-infinity diffeomorphism between the real line and the positive ray. And if you check, you will see that it induces an isomorphism between the Schwartz space of the real line and the Schwartz space of the positive ray. And note, and this is, so how to see this is true? So first you can calculate it. It's not difficult. But we can note that this phi is semi-algebraic, right? It's not just a C-infinity diffeomorphism, it's a semi-algebraic diffeomorphism. Right, it's definable in R, right? So it's okay. So the first result I want to show you is the following. So if we have a diffeomorphism that is definable in some polynomially bounded O-minimal structure, then it always induces Schwartz equivalent. Okay, and I hope first, it's highly believable, right? So if you do stuff with O-minimal structures and polynomial bounded O-minimal structure, you don't expect to have problems of pushing and pulling exponentially decaying function, right? So it's highly believable, hopefully. So in this seminar, I will not give any definition of O-minimal structure, and let me just remind that the O-minimal structure is polynomially bounded. If right, there are many definitions, and I hope not to make a mistake here, but the easiest definition is that if every definable function on the real line is bounded by a polynomial, right? That's a reasonable definition, maybe the easiest. So let's see how to prove this proposition, and then later we'll see other examples that are maybe somewhat related. So why this is true? So we need to define an auxiliary space that some people consider as important as a Schwartz space, but not me. So, but okay, let me give you the definition. So let's define what are tempered functions. So Schwartz functions are functions that, right, intuitively decay very fast at the boundary and at infinity. So tempered functions will be functions that maybe they're not bounded, maybe they explode, but not too bad. So let's see what I mean. So a C-infinity function on U is tempered. Again, U is open subset of Rn. if it satisfies the following two conditions. So first, if we take any multi-index alpha, and again, you should think of alpha as being a partial derivative, right? So you see this partial derivative in here. And if we take any point and think of points in the boundary, right? Like points not in the boundary are not interesting. And any point in the boundary, we can find an upper neighborhood of this point in the boundary and some integer such that this quantity is finite in this neighborhood. So let's see what's written here. So we evaluate the alpha derivative of t. So for instance, think of just the function t, alpha equals all zeros. And we multiply it by the distance to the boundary, but maybe we need to take the 100th power of the distance to the boundary, right? So this thing, just this thing, the distance to the boundary to the 100th power goes to 0 quite fast. So the condition is that we can find some fastness, some integer in here m, such that if we multiply this thing by t, we get a bounded thing. So you should think of functions that maybe they explode as they approach some point, but they explode like, I don't know, 1 over x or 1 over x to the 1000, but not exponentially. So this is the condition of being tempered at any boundary point if you want. And the second condition is quite ugly, but let me write it down. So the second definition is just being tempered at infinity. So if we look at, again, any partial derivative, we can find some integer and some big enough number r, the radius, such that if we look at points far enough from the origin, close to infinity, RT is bounded by either polynomial if u is everything, or this distance. And this distance is, you can believe me that it's equivalent to being the distance to the point at infinity if you want. So you can compactify, you can like one point rational compactification of Rn, and then this is kind of equivalent to saying that you're tempered in the sense of 1 at infinity. Okay, and I should say that this too is very, I mean, this technical ugly definition is very technical and ugly. So if you read the paper, and then they will give the reference to this paper. So there is a mistake in this definition, and hopefully corrigendo will be published soon. Okay, but don't be bothered about 2. So for instance, if you think about your u as being bounded, then 2 doesn't exist. And you can think of bounded sets, it's interesting enough. Okay, so this is the definition of tempered functions. And the space of tempered function is denoted by T. So we want to prove this lemma. We want to prove the lemma that if we have a definable diffeomorphism in some polynomial bounded on minimal structure, then it always induces Schwartz equivalence. Okay, great. So let's see what we have. We'll need 3 lemmas, and then everything will be very easy. So first of all, this lemma suggests a different way to think of tempered functions. Instead of saying that our function, if we have any function on U, it is tempered, namely it explodes, but not too bad, or maybe it doesn't explode at all, with all derivatives as we approach the boundary, if and only if it has the property that if we multiply it by any Schwartz function on U, we get a new Schwartz function. So maybe this direction is obvious, the other direction is also true. So if we have a function such that if we multiply it by, right, so we say that it acts like the Schwartz space is a module under pointwise multiplication, right? So if it's a function such that given any Schwartz function, if I multiply these two, I get a new Schwartz function, it must be tempered. Okay? And again, I hope it's believable. So that's the first lemma. The second lemma is very technical, but okay, it's important. Essentially, it tells us that we shouldn't worry too much about this Frechet space. We shouldn't worry about topology. So let me say what it means. It means that if I have 2 subsets, and me here is some map, and let's assume that me sends the Schwartz space of V to the Schwartz space of U. And I'm not saying it's an injection or bijection or whatever. Like it just sends it there. Then it's continuous. Okay, and this lemma tells us that if you want to show the two sets are Schwartz equivalent, it's enough to check that Schwartz functions are being sent to Schwartz functions, and Schwartz functions are being sent to Schwartz functions, and that's it. The fact that it will be an isomorphism of Frechet spaces is for free. And the third lemma, will be that if we have a C-infinity smooth function that is definable in some polynomial bounded on minimal structure, then it is tempered, right? And again, in this crowd, I hope it's highly believable, right? So a definable function, as you approach the boundary, cannot explode exponentially.
May I ask a question?
Yes, of course.
When you say F is definable, you also include that the domain U is definable.
Yes.
Do you?
Yes.
Okay.
Yes.
Okay.
Yes. Yes. But this is a great question again, because it will be related. So in a few minutes, we'll talk about cases in which our functions are in some sense definable, although the domain is not definable. And I'm not sure what I mean by this, but hopefully it will make sense. We will see some examples. Yes, but in this case, the domain is also definable.
Yeah, okay. Another little question.
Yes, of course.
When you speak on isomorphism between Fresh space, so for you, an isomorphism is supposed to respect the topology of the space, or is it an homeomorphism? Yeah, okay.
Yes.
Okay.
But again, lemma 2 tells you that it's not a problem.
Yeah, right.
Yeah.
So that one is.
And you mentioned that lemma 2 is very technical. It doesn't sound too technical.
No. I'm sorry. I apologize. It's not very technical. It's quite easy, but it's, if you don't think about these things in general,
it's certainly somewhat surprising, but yeah.
Yeah, it's very easy. It's very easy, actually. I mean, you just need to know how to choose the correct semi-norm to show that everything is okay.
Right.
But it's very easy. But let me add a remark. So your questions are really good because it just adds me to brings me to the next remark. So lemma 1 and lemma 2 hold for arbitrary open subsets. We don't need to assume anything about definability. So so this will be important later on. And lemma 3 essentially follows from Luyasevich inequality. So Luyasevich inequality tells us that if you have, again, I assume most people in the audience know, but if not, so Luyasevich inequality tells you roughly that if you have a definable function and you look how it grows, or in absolute value, how it grows as it leaves the zero set, then it must be growing in a comparable way to some polynomial. So for instance, you can't have flat functions. You can't have this exponent, right? You have this example in calculus 1, probably, I don't know, of an exponent that decays really fast, such that if you continue it by 0, you get a C-infinity function. So this cannot happen in a polynomially bounded O minimal structure, right? And this is, in some sense, Luyasevich inequality. And now that we have these three lemmas, it's quite easy to prove the proposition. So again, the proposition is we have a phi between two subsets. This is a definable C-infinity diffeomorphism. So U and V here are also definable. And I claim that it induces an isomorphism of Fresh spaces. Let's see why. So we take an arbitrary S in Schwartz function on V. And we need to show that if we precompose it with phi, we still get a Schwartz function, right? By lemma 2, this will be enough. We will also do the other way, right? But the argument will be symmetric. So what happens? So we look at this function. Quite easily, you will see that it decays as it approaches the boundary, right? Because this function S decays as it approaches the boundary. So this must too. So by the way, you see my cursor here when I move it, right? Otherwise, it will be very okay. And this function, so it decays. But what happens to derivatives? Well, when we will have derivatives, so we'll have, from Leibniz rule, we will have many summons. But how does each summon look like? It's by the chain rule, it's just the same function, maybe some derivatives of S, but S is a Schwartz function, so the derivatives will also be Schwartz functions. And maybe we'll have, the inner derivative, which will be all kinds of derivatives of phi. But from 3, the derivatives of phi, since phi is definable, are tempered. And from 1, if we multiply a tempered function by a Schwartz function, it is still Schwartz. All right, so that's it. We proved it. All right, it's proven, hopefully. Any questions about this argument? Okay. So let's proceed. Okay, so the next slide will be really, really fast. So all I showed you is this Schwartz equivalence of definable domains. And I don't want to tell you anything else about polynomially bounded or minimal definable things in this category, but I want to show you that other things exist. So I will just show you a slide with many, many things. So I just want to stress that there is some other things you can do with this theory, but I don't want to go into them today. So for instance, you can do the same thing for definable manifolds. So C infinity manifolds, definable in no minimal structures, whatever that means. And then you have many nice properties. So the assignment of tempered functions is a sheaf in the correct sense, right? So you will have like a Grothendieck topology or restricted topology. And the assignment of Schwartz functions is a flabby Kosheaf. And the assignment of tempered distributions. So tempered distribution is just the continuous dual space to the Schwartz space. So this is a flabby sheaf. And I'm not explaining what these things mean. I just want to emphasize that if you're interested in this business, there are other things to see. Any compactly supported function on these manifolds is Schwartz. In particular, if you have a compact manifold, any C infinity function is Schwartz.
Still a little remark, even if you want to go fast here. Just
Yeah.
so apparently, so the Schwartz function are not a sheaf. They're only a not a.
They are not a sheaf. They are a Kosheaf.
Kosheaf, yeah, because you
Yes.
use extension instead of restriction. Yeah, right. Okay.
Yes.
Okay, it's okay.
Yeah.
So sorry.
No, of course. If there are more questions, please stop me. It's better to do like only half of the presentation so people understand something than going over everything and only I understood. So this is another property. Another property is for any set, even if it's non-definable, you can always find a Schwartz function that is everywhere positive. I don't know. I like this property a lot. And the last one is that you can find the temperate partition of unity in my sense. So I think Andreas Fischer has a different sense of temperate partition of unity. But in my sense, these are C infinity functions that are in the usual sense of partition of unity. And this is kind of equivalent to just having Urison lemma, right? So if I have two closed subsets, I can find the tempered function that is 1 on one and 0 on the other, if they are disjoint. Okay, so let me proceed. And if you didn't understand anything from this slide, that's fine. Now I want to see what happens in the non-polynomially bounded structure case. So this will be very quick because it's very easy. Thanks for result by Chris Miller, that I think was here. I'm not sure. Right. So there is this dichotomy theorem saying that if we have a no-minimal structure that is not polynomially bounded, then the exponential function is always definable. And this is a very strong theorem in our context because it tells us that this whole Schwartz theory, it has no hope if we're talking about manifolds that are definable in non-polynomial bounded structures, because this example, that the first example, the non-example we saw, always exists in this structure, right? And I just want to add as a remark that even if we fix the embedding space, so here we have a problem of, we have two realizations of the real line, right? So the embedding space is not fixed, but even if we fix the embedding space, we can still construct bad things. So for instance, there is no partition of unity. Okay. I think this is all I wanted to say for the first part of the talk. Now I want to talk about a different scenario. And the second part is based on a work with Eden Prives. You'll see his name in a second. So let's go to the basic question, okay? So the basic question is as follows. This is the main problem. We have a C infinity smooth diffeomorphism. And we ask under what condition it induces an isomorphism of Richet spaces, right? So we saw one example. One example was if everything is definable in a polynomial bounded no-minimal structure, we won. But what happens in other cases? So let's see. So the first step will be that we remind ourselves lemma 2 saying that we really need to check just that phi pushes and pulls Schwartz functions to Schwartz functions, right? So we're in good shape. So let's fix a Schwartz function on V, right? So we have this phi from U to V, and we want to show that if we precompose it with phi, we get a new Schwartz function. So let's look at a very special case. Oh, let's just remind ourselves of the proposition. Instead of looking at the behavior at the boundary points and the Taylor series at the boundary points, we can just look at what happens to the function, in our case, which will be S composed with phi, precomposed with phi, and we can divide it by the distance to the boundary function, and we need to have these bounds, right? That's what we need to check. So let's just copy it. Okay, that's the same thing. So we have Schwartz function on V. We want to show that if we precompose it with phi, we get a Schwartz function on U, and this is enough to show that these bounds hold. So let's write it. So we have these bounds, right? These bounds come from the fact that S is just a Schwartz function on V, right? So if we take S, we divide it by the distance to the boundary in V to any power that we want, we know that this quantity is finite. And we want to show that the same thing holds for S precomposed with phi, right? So first, I want to note that if our phi only distorts the distance to the boundary polynomially, what do I mean by this? I mean that I can find two constants, positive constants, alpha and c, such that this distance that we found in this denominator is bounded by above by this distance. Oh dear, I didn't want to write the next line. Okay. For any point in the boundary, then we're in good shape, right? Because we want to show these bounds, and we have these bounds. So if we'll have these bounds, we can replace the denominator in here and get something similar to this expression. Does it make sense? Okay, great. And the good news is this thing holds for Helder maps. And of course, in this case, it will be by Helder, right? Because we want to have the symmetric argument from U to V and from V to U. Okay, and if you didn't think about analysis for a while, let me just remind you that Helder maps are maps that such that we can find two constants, alpha and C prime, such that for any 2 points in the domain, if we look at the difference between the images, it is bounded by this constant times the distance in the domain to the power alpha. And I'm writing, this is a technical remark, but it's nice, I think. So I'm writing alpha here like this alpha, because these two alphas will be the same. So the alpha Helder constant will give us this alpha in here, but the constant will be different. So, okay, it's not super important. Any questions on these steps? So again, we have an assumption that if this phi is by Helder, then at least the denominator can be somehow controlled. Still, we have a problem, because this proposition asserts that the function in the numerator, this S, is a Schwartz function on Rn, and the restriction to the complement is 0, right? So we still need to check that S composed with phi is a Schwartz function on the big space, right? So let's see. So we still need to check that S composed with phi extends to a Schwartz function. And let's assume that U is bounded, and also V. So if both U and V are bounded, then we only need to check that S composed with phi is a C infinity function, right? Because a C infinity function on a compact, on a bounded set is a Schwartz function. Now let's go to complex analysis, and let's assume, so instead of R2, I think of C. So so this phi is a map from C to C now. And let's assume that V is bounded, and also U. And let's assume that our phi is a conformal map. So if phi is a conformal map, we have the Cauchy's integration formula. And if you don't remember what it is, let's write it down, and you don't really need it, but you just need the upshot. So the upshot, my computer responds really, really slowly when is that we can take the case derivative of phi, and here the derivative, is with respect to the imaginary direction or the real direction, but since phi is conformal, then they are related, right? So it's not a real problem. So here I think of the phi as k as being either a number or a multi-index of two numbers, but it doesn't really matter. So we can write this formula. Hopefully this is Cauchy's integration formula. And then we just need to choose wisely this path that we take the integration on. And we take it to be a circle centered at z, right? We evaluate it at z, of radius, the distance to the boundary over 2. And this is always inside our domain, right? So we can take this integration, right? Because if we look at the distance and divide it by 2, we're guaranteed to be inside the domain. And then we get that the partial derivative of S compiles with phi go to 0 as Z approaches the boundary, right? Because again, what will happen is that we'll have, from the chain rule, we will have all kinds of partial derivatives of phi, but these are bounded by 1 over the distance to the boundary in some nice way. Okay, so we kind of proved, and if you didn't follow the details, then it's fine, right? The point is not like to check the proofs, it's just to illustrate some ideas, is that if we have a conformal bi-Helder map between bounded domains in the complex plane, then it induces an isomorphism of Rechet space. Okay, we kind of proved it if you believe all the steps. And in particular, and this is the result, the first main result of the paper with Eden. Eden knows complex analysis and he knows this stuff. So, okay. Is that any two bounded quasi-disks are Schwartz equivalent. Now, I didn't say what are quasi-disks. So we will try in 5 minutes to give like a, not a crash course, but a very, very, very brief review of quasi-conformal geometry. Before we do it, let me give an example. Okay, and this example shows that we didn't work for nothing. So the Koch snowflake is a quasi-disk. So and it's not definable in any minimal structure, right? So we didn't work for nothing, right? So you take an equilateral triangle, and on every edge you delete the middle 1/3, and you construct another equilateral triangle, and then you repeat this process infinitely many times, and you look at what's inside. So what's inside is a simply connected domain in the complex plane, and it happens to be a quasi-disk. So we proved that the Koch snowflake is Schwartz equivalent to the unit disk, which is nice. Now let me tell you very, very quickly what are these quasi-disks in general. So first, what is a quasi-circle? So a quasi-circle is a subset of the complex plane, such that if we look at its closure in time inside Riemann's sphere, right? So we take a 1-point compactification of the complex plane. So if we look at the closure, it's first a Jordan curve, and second, it has this regularity condition. So if we take any 2 points, we delete them from our curve, and we look at the diameter of the smallest connected component inside this J naught, without these 2 points, it is bounded by the distance in the complex plane. So let's say in Riemann's sphere, or you can take it in the complex plane, doesn't matter. But it has this regularity condition, so that the Koch snowflake satisfies, but other sets will not satisfy. Okay, so, and we will see examples. So you don't really need to think too much about this definition. You can just think that there is a definition about regularity in the boundary, and we will see some examples and counterexamples in a minute. So that's a quasi-circle. Yes. Yes.
Is it related to I don't know, quasi-conformal transformation of the complex plane?
Yes. Yes. Yes.
Ah, okay.
Yes. Yes. So the reason it is called quasi-circle because these are exactly images under quasi-conformal transformations of either the unit circle or just a line. We will see some examples. Yes.
Good.
But I will not go into it too much. In the paper, we use some of this theory because we have to. But yes. So this is a quasi-circle. A quasi-arc is just a subset of a quasi-circle, such that its closure inside the Riemann sphere is homomorphic to an interval. Okay, and it doesn't have to be connected. So for instance, if you look at 2 infinite rays that meet at infinity, sometimes there will be a quasi-arc. And again, we will see some examples. And the third thing is, so what is a quasi-disk? So a quasi-disk is a simply connected open subset of the complex plane if the boundary is a quasi-circle, okay, which is a nice definition. So let's see some examples. So the first example, okay, so the upper half plane is a quasi-disk, right? The boundary is just a nice line. If you look at its compactification in Riemann sphere, it's very nice. But the infinite open strip is not a quasi-disk. Why? Because the boundary consists of 2 parallel lines that meet at infinity, right? And at infinity, they meet in some cusp way. And in fact, any cusp, so if you look at domain that has an outwards cusp, whether if it's algebraic or exponential, it is never a quasi-circle. Because exactly you can take, so this is our cusp, you can take points that go to the cusp, and they will not satisfy this regularity condition. Okay, so cusps are not allowed, even algebraic. But if you take, for instance, the real graph of the sinus function, if you look at points on the real plane, such that the imaginary part is just the sinus of the real part, this will be a quasi-circle. It will be regular at infinity. But if you take the argument, instead of being the sinus of the real part, take it real part squared, this will not be a quasi-circle because now it oscillates like crazy at infinity. So it's not regular. Okay, these are just some examples to show you that it's an interesting field. I mean, you can do many things with this quasi-conformal geometry. So these are just some examples, but you can think about the Koch snowflake. And let me show you some other examples also in the quasi-conformal world. And I want to show you them not because they are important in this talk. Their proofs are important in this talk. And Lo, this is related to what you asked before. So let me show some things. So more diffeomorphism that induce Schwartz equivalence. So if we take any two domains such that they are the images of each other under a Mobius transformation, right? Just a rational function, a fine linear over a fine linear. They always induce Schwartz equivalence. And here I don't assume that U and V are definable. But Mobius transformation, okay, so this is one lemma. Okay, and they tell us that any two quasi-disks in general are Schwartz equivalent, because if you have a quasi-disk, let me remind you that we already proved that if they are bounded, they are Schwartz equivalent. So what do we do if they are not bounded? We just apply 1 over z minus z naught for some z naught far away from our set. And if you take a quasi-disk and you apply a Mobius transformation, you get a new quasi-disk always. Because Mobius transformation is in particular quasi-symmetry. Well, in fact, it's a symmetry. Okay. So we prove that any two quasi-disks in general are equivalent. And another example will be that if we take, and this is a very interesting example, if we take two simply connected domains such that one is the image of the other under a holomorphic square root. But again, I'm not assuming anything about our domains. Maybe they are terrible. Maybe they don't contain they are simply connected. They don't contain the origin, but maybe they're spiraling around the origin infinitely many times as you go to the origin, right? So maybe these are terrible, terrible sets, not definable in any. So in the quasi-conformal world, you can construct sets that are infinitely many, that spirals infinitely around the origin. But still, if there is a holomorphic square root, it induces a Schwartz equivalence. And then you can derive, for instance, that if we have a domain whose boundary is a quasi-arc, then it is always Schwartz equivalent either to the disk, if the quasi-arc, the boundary is unbounded, or to the complement, to the closure of the disk, if the boundary is bounded. But again, forget this corollary and theorem. They're not important. The important thing are these two lemmas. Right, so let's look at the second. So the first lemma, you can say, well, you're cheating because, in fact, a Mobius transformation can always be extended to a bigger domain that is definable, right? Just take, for instance, in this example, take the complex plane without z naught. It's a definable set, definable in the real line, right? You don't need to add anything, and now everything is definable and nice. And thus this U and V happens to be like weird subsets of this definable case. But what happens in the second lemma? So in the second lemma, if you take this infinite spiral, it doesn't extend to anything reasonable. But still the definition like locally is given by some formula that is definable. Right? Maybe this formula oscillates infinitely many times, but a square root is a square root. There are only two formulae for these, right? So these two lemmas just tells us that maybe we were just scratching the surface with these two lemmas. Maybe we can say something much more general if we assume something about the maps, if they are given by, I don't know, for instance, finitely many formulae definable, and maybe the sets are not important, right? But I can't really say it because I don't know, but it seems that there's something there, right? Does it make sense somehow? Yeah. Okay, now let me finish by just showing some other examples and non-examples that are kind of new. So first, let me show you why this. So we saw, before I'm showing you this example, we saw two examples, right? So the first example was related to model theory, right? We said if we have something that is definable in a polynomially bounded or minimal structure, then this diffeomorphism must induce Schwartz equivalence. And we saw a different approach, that is, if we have something that is kind of in the quasi-conformal world, then we can also say it induces Schwartz equivalence. So let me show you an example that is neither there nor there. So let's look at this example. So we take all points in R2, x goes from 0 to infinity, so it's a strip. But instead of taking just a uniform strip, y is bounded between 0 and e to the minus x, right? So this set, well, it's not definable in any polynomially bounded or minimal structure, right? I hope it's right. And it's also, it's not a quasi-disk because it has this terrible cusp at infinity, right? But still, we can show that this set is Schwartz equivalent to the unit disk. Okay, so this example is important because it shows us that we have some sufficient conditions to things are Schwartz equivalent to the unit disk, but we are very far from having sufficient conditions. So I have like 5 more minutes, right? Am I okay? Great.
Yeah, 4.
4. Okay. Okay. In my resolution, it's the same. Okay. Okay. So this is the first example. So the question you may ask, and this is a question. So I gave a similar talk in this seminar in the summer of 2020, and then we ended with this question. Maybe if we have two subsets that are C infinity diffeomorphic, maybe they are always Schwartz equivalent. Maybe in fact, we just need to find the right diffeomorphism, right? It's like on the complex plane, we know that any two subsets that are right simply connected, well, proper subset, not the whole complex plane, we know that they are holomorphically equivalent, right? This is Riemann's mapping theorem, right? Not any map is holomorphic, but Riemann tells us how to find this holomorphic map. So maybe it's the same case for this Schwartz business. And now we can say that the answer is no, because we have a counterexample. So let me show you the counterexample really quickly. I will not prove the example, but you can believe me if you want. So let's look at this example. So this is by Nazarov, Fedor Nazarov gave us this example, constructed this example. So I will just tell you what is the set. So let's look at this union of disks. We have infinitely many disks. I just want to say that the fact that this set is unbounded is not important. We can construct the same thing with a bounded set. So it doesn't have to be anything with infinity. So we take a countable union of disks around the natural numbers, and the radii decay like 1 over n squared. Okay, so these become smaller and smaller. And we connect them with these tubes, right, which are Cartesian product of n plus 1. So these are these tubes. And the width of these tubes decay really, really fast, right? So the width is like super exponentially or double exponentially small. And it happens to be, so this set is simply connected proper open subset of the complex plane of R2, if you want. So Riemann's theorem tells us that there is a holomorphic map between this set, in particular it's C infinity, to the unit disk, right? But we can show that no C infinity diffeomorphism between this set and the unit disk induce Schwartz equivalence. So in particular, the Schwartz space of this set is not equivalent to the Schwartz space of the unit disk. Okay, which is very nice. We were very happy to find it. We have some other examples, new examples, but I think one is enough. And let me just end by so we had this question. Right, any two C infinity diffeomorphic subsets are Schwartz equivalent. We know that the answer is no. So this is the question we're left with. So under what conditions two C infinity diffeomorphic subsets are Schwartz equivalent? This question seems to be, I don't know, too difficult maybe, but maybe as a first stage, we'll be happy with, let's take a simply connected open proper subset of the complex plane. So we know it's C infinity diffeomorphic to the unit disk, but under what conditions this set is Schwartz equivalent to the unit disk. So this is like the first question we would like to answer. I don't know how to answer it too, but okay. Okay, so thank you for listening. And I think I'm right on time. Patrick, am I okay?
Yeah, right on time.
Okay.
Thank you very much.
Thank you.
And
Thank you.
Since this is the seminar, we have a little bit of time for questions before the question session for the course. Any questions?
What?
Yes.
Ari, could you give us a hint of how you show that no C infinity Schwartz equivalence exists for the Nazarov example? 2 minutes
Yes.
of hint.
Yes, in 2 minutes I can give a hint, definitely. So let's look at this example. So let's look at this set. So we do the following. Inside of each disk, we look at the half disk. Okay, so it's a disk of half radius, and we look at its closure. So it's a compact subset of this disk, right? And then we first construct a Schwartz function that is somewhat big on this compact, right? So we have this compact, and we have another compact in here, and we have another compact in here, and so on. And we look at and we claim that there is a function that gets the value e to the minus n on each of these compacts. Is it believable? So it decays exponentially, and it's completely supported. No, it's not completely supported in infinity, but it's away from the boundary, right? And it's identically zero outside these compacts. So this is a Schwartz function. Now you give me any C infinity diffeomorphism between this set and the unit disk, right? So let's look, where does these compacts go under this C infinity diffeomorphism? From knowing that we have this specific Schwartz function that we constructed, we can say something about where these compacts go on the disk, right? Because it decays like e to the minus n. So in particular, these compacts on the unit disk should go to the boundary of the unit disk. And we can also say something about how fast or how slow they go to the boundary. So we can control everything. And then we construct a different Schwartz function on the disk in a very simple way. We just take this, the first bump function you see in life, right? So this, the symmetric Schwartz function on the disk. And so now we know two things. We know first where these compacts are on the disk. And second, we know that there is this very easy Schwartz function on the disk. Now we look, where does what are the values that this Schwartz function on the disk gives us on these compacts in here, back to the original compacts. And we can say something about how big it is. And now finally, we use the fact that we can connect nicely these compacts on the disk. And then the image under this diffeomorphism will be lines through these tubes. And this gives you a contradiction, because you will know the values on these lines in the disk, and then you will know the values on the lines in these tubes. And these values will be too big, because you know that these tubes become really, really small fast. So the distance to the boundary on these tubes becomes really, really small, really, really fast. I'm not sure if it's comprehensible, but yeah, that's the basic idea. It's very clever. It's not due to us. It's due to Nazarov. So, or maybe Sodin worked with him on it. I'm not sure. I think Nazarov constructed this example. Yeah, but maybe I should say that we also have an example in one dimension. So we can show that like a countable union of intervals, two countable union of intervals are not always Schwartz equivalent. We can construct counterexamples similar to this example. And maybe I should also add that usually my typical example for candidate for non-Schwartz equivalent sets was take just the real line without z, without the integers. So that's like the easiest countable union, right? and take the unit interval without the counter set. Right, so that's also a countable union of intervals, but with weird behavior. And we can show that these two things are Schwartz equivalent, which wasn't what we expected, but now we can show it. We can construct a diffeomorphism that induce Schwartz. Yeah, this was very disappointing and also made us very happy because, okay. I'm not sure what's more.
Thank you.
Thank you.
Any last questions?
Yeah, is it obvious to see why the Koch snowflake is a quasi-disk? Is it easy to see?
For people that are doing this quasi-conformal stuff enough, it's very easy. For me, it's not easy, but
Okay.
essentially you get. I hope I'm not saying things that are completely wrong, but you have this fixed angle, right, in the Koch snowflake. So this fixed angle will tell you something about the diameter. So you take 2 points on the snowflake and you delete them, right? And then you want to know what's the diameter of this, of what you're left with, right? A small piece, and you want to control it by the usual distance, right? And the fact that you have this constant angle in each iteration will give you a way to bound this thing inside the disk in not a terrible way. So if you take the snowflake with angles that become steeper and steeper, I think this will not be a quasi-disk, right?
Okay, see. No, I agree. No, because I was puzzled by the fact that this snowflake is a quasi-domain and that, for example, the graph of sinus of x square is bad. I could not figure out what, but it probably this constant angle, which is the main reason.
Yes.
Okay.
Yes.
Okay.
And sine of x squared, it's quite easy to see because you have oscillations. You don't really need infinity. You have oscillations that become denser and denser, right? So you can take 2 points on this graph, and they are arbitrarily close to each other, but the distance inside the graph, right? The diameter of the graph will be like a whole iteration, right? So it will always be 1, but these points go to 0, right? So this can never happen. Yeah, and the reason I'm showing this Koch snowflake is because, again, this was a candidate for 2 sets that are not Schwartz equivalent, the unit disk and the Koch snowflake. I was sure that they are not Schwartz equivalent, but I'm wrong. Yeah, but I can prove that I'm wrong, right?
Thank you.
Okay, well, let's thank the speaker again. So I will stop the recording.